on, we are in the last group from this section to report about chapter 15 or testing, debugging, and verification. So first, we have the introduction. So testing chips must be verified, and this testing accounts for is more effort than the functionality test and logic verification. Next, we have the silicon debug, and the third is the manufacturing test. So in the functionality test and logic verification, we have to run before it came out to verify the functionality of the circuit. And for the silicon debug, I run in the first batch of chips with the third from fabrication. These tests confirm that the chip occurs as it was intended and not debugged in this purpose. So they can be much more extensive in the logic verification test because the chip can be tested at full speed in the system. For example, a new microprocessor can be placed in a prototype motherboard to try to boot the operating system. It requires creative work to locate the loss of layers because the designer has much less visibility into the fabricated chip compared to during test design verification. So last is the manufacturing test. It is to verify that everything in store, be it a storage element, in the chip functions correctly. So these tests are conducted in each manufactured chip before shipping to the customer to verify that the silicon is completely intact. Next we have here. Here in the chapter, we will examine a number of mechanisms. So the goal of the manufacturing test procedure is to determine which die are good and should be shipped to customers. So this shows the amount and the levels that must a chip undergo in the testing process. Next, when a chip returns to fabrication, the first set of tests are run in a lab environment. So you need to prepare for this event. You can begin by constructing a circuit board that provides the following attributes. First, we have the power for the IC ability to vary dB and measure power dissipation. Next, we have the real-world signal connections. For example, the analog and digital inputs and outputs as required. So, the third one is a clock input as required. It is helpful to have a stable variable frequency clock generator. And last is the digital interface to a PC. Either serial or parallel ports for slow data or PCI bus for fast data interchanges. So we have the second manufacturing test. We have a debugging. So there is a nine debugging principles. First, we must understand the system. Next, make it fail. Find a way to elicit the bug where repeatable method is preferable. Third is quick thinking and loop. Fourth is debugging over. Fifth is change one thing at a time. Next, keep an audit trail. Next, we have check the log, get a fresh view, and if you didn't fix it, it needs fixed. Okay, for the most part, if a digital chip sign waits at the gate level and passes sign analysis checks during design, it will do exactly the same in silicon. Possible deviations from the simulated circuit occur in the following cases. First condition, if a circuit is slower than predicted, we must fix it. We must slow clock or raise the VDD. Next, if the circuit has a raised condition, to fix it, you must keep with heat gun if a logic gate cost raised. Next, the third one is if a circuit has dynamic logic problems, we must also fix it, of course, if the process is don't do it again. So the next is morally crosstalk problems. So to fix it, we must get better tools. Next, if there is a wrong functionality to fix it, we must do a better job of verification. The manufacturing test. So the typical defects include the following. First is the layer-to-layer shorts or the metal-to-metal. Next is the discontinuous wires. For examples, metal beads when crossing vertical topology jumps. Third is the missing or damaged bias. Next, we have the shorts from the clean gate outside the substrate or the well. Next, this in turn lead to particular circuit maladies, including the following. First, the node shorted to power or ground, the node shorted to each other, or the inputs floating or output disconnected. So apart from the verification of internal gates for the input-output integrity is also tested with the following tests being completed. First is the input-output levels. For example, it is checking the noise margin for TTL, ECL, or CMOS ion pads. Next, we have the speed test. Take note, In general, manufacturing test generation assumes the function of the circuit or chip is correct. It requires ways of exercising all gain inputs and monitoring all gain outputs. Next we report is about the tester, test fixtures, and test programs that are reported by one of the group named Mr. Michael Engr, GPR.
Again, for the next topic, which is the testers, test fixtures, and test programs. In a production, after fabricating a product, it will undergo a series of tests. In our topic, after a chip is fabricated, it will undergo also a test program and testers and test fixtures. So what is these testers and test fixtures? A tester is a device that can apply a sequence of stimuli to a chip or system under test and monitor and record the result of those operations. Testers come in various shapes and sizes. We will concentrate first on the cases where a general purpose production tester is to be used. Production testers are usually expensive pieces of equipment with configurable input-output ports and huge amount of RAM behind. The tester drives input pins from this memory on a cycle-by-cycle basis and samples and stores the level and output pins. Next, four general types of test fixtures. First is a probe card test at the wafer level or unpackaged die level with a chip tester. Next is a load board test package or with a chip tester. Next one, a printed circuit board for bench level testing with or without a tester. Last is a PCB with a chip in situ, demonstrating the system application for which the chip is used. Next is the test programs. After the product undergoes the tester, the test program will record and the system is made by programming. So, what is this test program? The tester requires a test program in verification and test. This is an overloaded term. This program is normally written in a high-level language. For instance, the image language used by Teradyne is based on C. That supports a library or primitives for a particular tester. Setup. First, setup is to set that supply voltages. Next, assign mapping between stimulus, files, signal layers, and physical tester pins. Next is set the pins on the tester to be input or output and their VOH or VIH levels. Next is set the clock on the tester. Last is set the input pattern and output assertion timing. Next, apply supply voltages. Apply digital stimulus and record responses. Next, check responses against assertion. Last is report and log errors. Last is the handlers. An IC handler is responsible for feeding ICs to a test fixtures and attached to a tester. So, if you will imagine, there is a chamber which the product will be placed there, and the handlers will hold the chip for the chip will not be damaged or any affected by errors, human errors. So the next topic will be discussed again by Jerboy.
Okay, so the third topic will be the logic verification principles. With VLSI, CBN network with N equals 25 and M equals 50 or two array defined patterns, which is approximately 3.8 times 10 raised to 22, assuming one pattern balance, and apply them with an application rate of 1 microsecond per pattern. The test will take over a billion years. So this figure shows the computational explosion in test vectors. So what is test vectors? The test vectors are a set of patterns applied to inputs and a set of expected outputs. So both logic verification and manufacturing tests require a good set of test vectors. The set should be large enough to catch all the logic errors and manufacturing defects, yet small enough to keep test time and the cost reasonable. So we have the most common types of test vectors, namely directed and random variables. So first we have the directed vectors. The directed vectors are selected by an engineer who is knowledgeable about the system. Their purpose is to go over the corner cases where the system might be most likely to malfunction. For example, in the 32-bit data path, likely corner cases include the following. So these are the following corner cases. So for all zeros, we have 0x, then 1, 2, 4, 6, 8 zeros. Then for all ones, we have 0x, and then 8f. So we have also the test benches and harnesses. So verification test bench or harness is a piece of HDL code that is placed as a wrapper around a core piece of HDL to apply and check test vectors. In the simplest test bench, input vectors are applied to the module under test, and each cycle, the outputs are examined to determine whether they comply with the predefined expected data set. So the expected outputs can be derived from the golden model and saved as a file where the value can be computed on the fly. So simulators usually provide settable breakpoints and single or multiple stepping abilities to allow the designer to step through a test sequence while debugging discrepancies. Next we have the regression testing. So high-level language scripts are frequently used when running large test benches, especially for regression testing. So regression testing involves performing a suite simulations to automatically verify that no functionality has inadvertently changed in a module or set of modules. So during design, it is a common practice to run a regression script every night after design activities. Apple will check that bug fixes or feature enhancements have not broken completed modules. Next we have the version control. So the version control combined with the regression testing is the use of versioning, or that is the orderly management of different design iterations. Unix or Linux tools such as CMOS or Subversion are useful for this. Next, we have the backtracking. So it is the same as the one in debugging. So it is another important tool to use during verification, and in fact, the whole design cycle. It is a bug tracking system. So a bug tracking system as the Unix or Linux-based GNATS allow the management of a wide variety of bugs. So in these systems, each bug is entered and the location nature is inverted the bug noted. So for your information, the bug that is noted here is not the bugs that we are concerned. So the bugs are those discrepancies in the system. So, and the bug discovery is noted along with the perceived person responsible for fixing it. So next we will have the next reporter to discuss about the silicon developers. So may I present to you Mr. Captain Knows to report about silicon developers.
So let's proceed to the next topic, the silicon development. Debugging is when the chip operates incorrectly, but you cannot ascertain the cause by making measurements at the chip pin or scan chip outputs. There are techniques for directly accessing the signal where specified signals can be brought to the top of the chip as probe points. Next is the overglass cut mask through the fault is known, a focus ion beam or FIB can be used to cut wires or namely conductors down. Smoke plugs. It is made with voltage on one axis and speed and other. The test vectors are applied at each combination of voltage and clock speed, and the success of the test is recorded. Then often, only a set of vectors of the particular module is applied to diagnose a problem in that particular module. So in this figure, this is the smoke for Intel Atom microprocessor. That's in the light gray area indicate correct operation, while different letters indicate different failure modes. The chip works at 1.25 gigahertz at 0.75 volts and at 2.5 gigahertz at 1.25 volts. A smoke and also plug operating speed against temperature. At cold temperature, FETs are faster, have lower effective resistance, and have higher threshold voltages. A normal smoke should show speed increasing as temperature decreases. So the next reporter is John Mark Sawyer.
Sure.
Good afternoon. So, 15.5, manufacturing test principles. So, the purpose of the manufacturing test is to screen out most of the defective parts before they are shipped to customers. Typical commercial products target to the rate of 3 to 1,000 defects per million BP or DPM chips shipped. So, in this figure, figure 15.10, you will see the different effects in manufacturing. We have the metal shell ring, metal film particle, open defects, spongy metal missing pattern, spot defects, metal block, edge. So, fault models. To deal with the existence of the good and bad parts, it is necessary to propose a fault model. Example, a model for how faults occur in the impact on circuits. So we have stack faults and the letter B, short circuit and open circuit faults. So these are the factors to be considered. First is the observability. Observability of a particular circuit node is the degree to which you can observe that node at the outputs of an integrated circuit. Example, the pins. This metric is relevant when you want to measure the output of the gate within a larger circuit to check it operates correctly. So the second one is the controllability. The controllability of an internal circuit node within a chip is a measure of a list of a setting the node to A1 or 0 state. This metric is important when assessing the degree of difficulty of testing of a particular signal within a circuit. An easily controllable node will be directly settable via an input pad. The next one is the repeatability. Repeatability of the system is the ability to produce the same outputs of the given same parts. Combinational logic and synchronous sequential logic is always repeatable when it is functioning correctly. However, certain asynchronous sequential circuits are non-deterministic. Next one, survivability. The survivability of the system is the ability to continue function after a fault. For example, error correcting codes provide survivability in the event of the soft errors. Redundant rows, columns, and memory spare cores provide survivability in the event of manufacturing defects. So, the next one is the fault coverage. Fault coverage, measure of goodness or the set of test vector is the amount of the fault coverage it achieves. So the next one, the next part is automatic test pattern generation or ATPG. Commercial ATPG tools can achieve excellent fault coverage. However, they are computation intensive and often must be run on the servers to print parts with many parallel processors. Some tools are statistical algorithms to predict all the fault coverage of a set of vectors without requiring as much as simulation. Next part, design of the testability. So, design of the testability. The keys of design circuits are the testable or controllability and observability. This stated, controllability is the ability to set 1 and reset to 0 or to 0 in every node internal to the circuit. Observability is the ability to observe either directly or indirectly the state of any node in the circuit. Good observability and controllability deduce the cost of the manufacturing test because the allow high fault coverage in the relativity to test vectors. Moreover, they can be essential to silicon debug because physically probing internal signals has become so difficult. So we have this part, we have the ad hoc testing, the scan-based approaches, and the built-in self-test or BIST. Ad hoc testing. In ad hoc testing, we have the four categories. We have partitioning large sequential circuits, adding the test points, adding the multiplexers, and lastly, providing the easy state reset. Scan design. Scan design strategy for testing has evolved to provide observability and controllability of each register. In these designs, we scan the register operate with 1 or 2 modes. In normal mode, they behave as expected. So we have figure 15.16, the scan-based testing. So this is the figure. We have the scan in, the inputs, and the scan out. So the other one is the parallel scan. And the scannable register design. So the third, built-in self-test or BIST. Self-test and built-in test techniques as their name suggests rely on the augmented circuits to allow them to perform operations upon themselves to prove the correct operation. These techniques are added area to the chip for the test logic because but reduce the test time required thus and lower the overall system cost. So under BIST, we have BIST itself, memory BIST, and the last one on the other on-chip test strategies. IDTQ testing. IDTQ testing can be completed internal to the chip by measuring the current drawn on the VDD line or internally using special contracting test circuits. So this technique gives a form of indirect massive observability at a little circuit overhead. Design for manufacturability. Number 1, physical. At physical level, the yield enhanced manufacture can be improved by reducing the effects of the process defects. Second, redundancy. Redundant structure can be used to compensate or defective components on the chip. For example, memory arrays are commonly built with extra rows. During the manufacturing test, if one of the words is found to be defective, the memory can be reconfigured to access the spare row instead. Number 3, the power. So, this is another factor. Limited power can cause failure due to the excess current in wires, which in turn can cause metal migration failures. In addition, high power devices raise the die temperature, degrading the performance over the time, causing device parameter shift. Fourth, process spread. We have seen that process simulations can be carried out at different process corners. Multi-color analysis can be provide better modeling for process spread and can help with the centering design within the process variations. Fifth, yield analysis. When the chip pass for yield or will be manufactured in high volume, thus the failed manufacturing test can be taken to a laboratory for yield analysis to locate the root cause of the failure. So this is the boundary scan. So testing in the university environment. So to be discussed by Mr. Biray.
Next topic is about boundary scan. Up to this point, we have concentrated on methods of testing individual chips. Many defects occurs on the levels of the chip. And in the open and shorted circuits on the PCB. So, the IEEE 1149 boundary, an architecture is shown on the figure. All of the input-output pins of each IC on the board are connected serially in a standardized scan chain, accessed through the test access port, so that every pin can be observed and controlled remotely through the scan chain. At the board level, ICs obeying the standard can be connected in series to form a scan chain, spinning the entire board. Connections between the IC are tested by scanning values into the output of each chip and checking that those values are received at the inputs of the chip they drive. Testing in a university environment. Industry environments are usually well funded and the appropriate testability tools are available to ensure a product grade test effort. But what do you do in a university environment when the infrastructure might not be quite as affluent as in the industry setting? Not only may test tools be available, but also the very act of building a test board can be dumping extra amount of work on top of the chip. For a start, the integrated environment available for most IC design flows allows the designer to simulate the test circuitry. So while it might be seen superfluous to the test at hand, including test circuitry can save a huge amount of effort after the chip returns. Moreover, on-chip circuitry can often test at speed that are impossible off-chip without extremely expensive production test machines. The main point is to think ahead. Next is pitfalls and fallacies that will report by Leo.
So for the last topic, the pitfalls and fallacies. Pitfalls and fallacies is a product in the field has unpredictable. A microprocessor had been in the field for several years when reports began arriving from major customers that certain programs would cause the system to have an unpredictable time switch interval of hours to days. The manufacturer appointed a tighter team to resolve the error. The hang rate proved to be insensitive to power supply voltage, operating temperature, and clock rate. Next, a product fails after the manufacturing process matures. The team negotiated to order several thousand units of the discontinued microprocessor before production was shut down. The data communications product becomes successful and was shipped in large quantity. After it had been in the field for some time, major customers reported that the product would crash in large networks. A wasted speed. A microprocessor was taken out and came back nearly fully operational. Minor changes were made to the layout and documentation was developed. Then a second revision was taken out. The second revision came back completely non-functional with a short between power and ground. Optical inspection while manufacturing the polysilicon layer showed that there was no field oxide on the chip. At high voltage, a chip only operates at low frequency. While booting the operating system during silicon debug, a microprocessor operated as expected at low voltage. At high voltage, the part only function at low frequency. The high voltage group is an indication of a potential coupling problem in which the coupling is exacerbated by the fast edge rates associated with high voltage operation. Next is the insufficient simulation. A ring oscillator was placed on the chip as a test structure to verify that the hardware was at least partially functional, even if the rest of the chip might not work. It didn't oscillate. It had not been simulated because it was too simple. Incomplete top-level verification. The RC simulation were not performed on the connections to the pads. So, students carefully scrutinize their routing by hand. Upon testing, three of the 4 different designs were found to have errors in the routing to the pads. A neural network chip seemed to have a defective scan chain because the scan data outline never budged from 0 as configuration data was scanned into the chip. Then, after a look ahead, other produced incorrect results on certain input patterns. The least significant bits were always correct. Then, a GPS searcher chip had an inverter connected to a pair of pins to verify that the chip showed basic functionality.
That is a chapter 15 from the VLSI CMOS design. Thank you for listening.
Kim,